Hello friends, welcome to lesson 2.7 from Brian Passwater's AP Precalculus material. Today we're going to be talking about compositions of functions or composite functions. It's a topic that I'm pretty sure is covered in Algebra 2, but covering it here in review anyway, because it does come up, so it should be covered. So basically, right, how do functions work? Again, best way to think of a function is just as an input-output machine. There's some number that you put in, or something, doesn't even have to be a number, something you put in, and then there's something that comes out. Sometimes you're given the equation, so you see what the machine looks like. So in this case, our machine is f of x equals 2x minus 3. X means the input, and then the f, right, if you say f of 2, that means like what's the output. So in this case, f of 5 is going to be 2 times 5, whoops, I'm not writing, let's see, 2 times 5 minus 3, and this is going to be 7. Okay, f of c is going to be 2 times c minus 3, and that's it. You can't simplify the expression any more than that. F of 4a, so we do 2 times 4a minus 3, so this is 8a minus 3. And again, that's it. You can't simplify anymore. So again, the input, if you give an input of 4a, the output is 8a minus 3. And then if you have f of 5x minus 1, what you've got now is basically like you've got another function, 5x minus 1, and that whole thing is being put into f, the f function, right? And so this is 2 times 5x minus 1 minus 3, right? That's how it works. So this becomes 10x minus 2 minus 3, so 10x minus 5. And so that's the output when you put in that other whole thing, which is its own function, 5x minus 1. And so we can do this. We can take an entire function and put it into another function. And if we know how the machine works, right, if we know the equation, what the machine looks like, then we can see what it looks like when you put the two machines together, the two input-output machines. So sometimes in math we plug a value in for x into a function, and then plug that value into another function. Just to use the example they give us here, let g of x equals 3x plus 1, and let g of 2 equals c. And they want to say find g of c. Okay, and so g of 2 equals 3 times 2 plus 1. And so this gives us 7, and that's equal to c. So then if we put c in to this now, right, 7 is c, so we're going to find g of 7. That is going to be 3 times 7 plus 1, so that'll be 22. So what do we do? First we found g of 2, and then we put that in, right, to figure out what c was. And then when we have c, we can use c, 7, as our input, again, into the function, right? And so there are two ways to write composite functions. One of them is like this, f g x, right? So that's f of g of x, or f of g of x. That second one is a little bit clearer because you can actually see g of x is like in the parentheses of f of x. So we read this f of g of x. That's how we read that. Okay, so when we work with composite functions, we start on the inside, or the right? And so if given f of g of x, first we evaluate g of x, and then we use the answer from g of x and plug it into f of x. Just like, again, you've done this before. So if we're given these two functions, f of x is 3x minus 5 and g of x is 2x plus 1, evaluate the following expression. So f of g of 3, so first we find g of 3, and then we find f of 7. Very simple, right? But we're going through the examples anyway. So we'll give this one a shot. So first we plug 3 into f, and then we take that result and put it into g. So for b we get 9, and C, f of 4. So here we plug 4 into f, and then whatever we get as the output, we put that back into f again. Right? And 16 is the answer to that one. Here's another example. Right, so using the same equations from f and g, find expressions for the following. So now we just plug in g, we plug in that whole function as the input for f. So f of, and now g of x is 2x plus 1 is going to be, so f of x is 3 times, now I just plug this whole thing in, 2x plus 1 minus 5. Simplify. And then we do the other way. So we plug the entire function f of x in for g of x, or into g of x, I should say. Another example, using the same idea, we're given 4 different functions, and now we're going to find the following. All right, either an expression or an actual value. So for k of h of 2, I take 2, I put it into h, I take that result, put it into k. And we get 10. For the next one, that is read h of m of negative 1. Right, first time seeing that notation. So I put negative 1 into m, take the output from that, and put that into h. Okay. And we get negative 5. K of p of x, so I take x, I put it into p, and then that output, which is itself going to be an expression, I put that into k, and then simplify, and that's my answer. And so that's the expression that we get at the end. It's messy, but we can't simplify anymore, so we leave it. And then here's another example. We don't always have to have equations. Again, sometimes the output machine, you don't see what the function is, but you're just given a graph or a table, but all the same rules still apply. Even k of x, what I would recommend for k of x is actually to write out what the expression looks like, because it says it's a quadratic function with a horizontal translation of 2, followed by a vertical translation of negative 3. You could do that manually, you could say, each time you have a number, but you can take that and actually find an expression for it. So this k of x is going to be, so a horizontal translation of 2, side to side. If you're going to the right 2, right, plus 2, then you actually put in negative 2, like that, so this is squared. And then a vertical translation of negative 3, we just tack that on negative 3. That'll take whatever graph we get and shift it down negative 3. Okay, so now I have an expression for k of x, and that's going to be helpful as I go through these examples. Nothing very different from what we've done before. Again, like A, I'm taking 3, putting it into G. I'm taking that output and putting it into F. Okay, and sometimes I don't have an equation. I'm just using these other graphs and stuff, right? So G of 3. So when I get this, so when I put in 3 for G, I try to do that. Notice that there is no input for 3, right? So it's not defined. And so if I have undefined for G, I can't put undefined back in for F. And so the answer to A is just that it's undefined. All right, so now this is H of F of 8. So my first input is 8, right? I'm putting it into F. So I go over here to 8, and I get negative 1. Okay, so now I'm finding H of negative 1. And going over to H, right? If H is negative 1, so that means I'm going to be using this expression and plugging it in here. So I'm going to put find the absolute value of negative 7 plus 3 times negative 1. Find the absolute value. Simplify. And I get 10. Okay. G of k of 0. So I put 0 into k, and then I put that output into G. So k of 0 gives me a value of 1. But the problem is then when I go over to G, there's no available input of 1. It's not defined. And so the answer is, for this, not defined. G is giving us a little bit of trouble, so we got to pay attention as we do that one. For D, f of 2, so input into F, and then whatever output is, I put that back into F. Let's see what happens, because this is the graph. So an input of 2, input of 2 gives me a value of 1. So now I'm going to find f of 1. All right, so let's see. If I have an input of 1, I get 4. Okay, so g of h of 1, let's see if g gives us anything this time. So I go to h. First I'm going to find h of 1. So h of 1, when I'm plugging in 1, oops, if I have an input of 1, then it's just negative 4. So I'm going to put here negative 4. And so then I get g of negative 4. So when I look for the input of negative 4, it's here, and the output is pi. So this is, g of negative 4 is pi. Okay, f. Now we've got a bunch. It's like all the functions were being used. So what do? We plug 3 into k, take the output, put it into h, take that output, put it into f, take that output, put it into g. And we'll see if g works out for us this time like it did for the last one. So first of all, k of 3. All right, so that's this expression, x minus 2 squared minus 3. So k of 3 is 3 minus 2 squared minus 3. So 3 minus 2 is 1 squared, is just 1. So negative 2, h of 2, h of negative 2, I should say. So I look for h. When I have an input of negative 2, I'm going to be using this part of the function. So negative 7 plus 3x. So 3 times negative 2 is negative 6. So I end up with 13, absolute value of negative 13, which is just 13. So now I need f of 13. And my graph doesn't go out to 13. I'm looking here at f, and there's no value over here. I'm looking at this graph, and there is no value beyond 10. There's no input beyond 10. And so f of 13 is undefined. So there is composite functions, compositions of functions with a ton of practice to help reinforce the idea. Thanks for watching. Don't forget to like and subscribe.